Hello. So the purpose of this video is to sort of grease the wheels a little bit for you in doing the final course project for differential equations. And so I'm hoping that you've been to the Canvas page and looked at the assignment and found this video, and you've downloaded the starter file. So this is on my desktop, course project math 4th IPython notebook, IPYNB. All right, so I just saved that to the desktop, but wherever you want to save it, just make sure you can actually find it on your computer. Okay, so you can see I'm on the Google, and we're going to navigate to a website called JuliaBox. Okay, so you can see I'm just Googling it. Go here, and I'm going to see if I can start a new account. I already have an account here, but I want to show you the whole process. So you can see it's going to be defunct soon, but not yet. So we can still use it for this class, which is great news for me. I will say that what you're going to learn in this is a free software called Julia. And this is an online version of it that you can run for free. You can see why they're going out of business is that, they didn't make money from corporations or something. However, I will say, if you become interested in this, it's a outstanding programming language that can do many things that MATLAB and other things can't do, and it's totally free. So if you Google Julia Pro, you can see that they link to it here. Then you can download sort of all the stuff you need to your computer and run it on your actual computer. Now that's not required at all for the class and for this project, which is why we're going to run it in JuliaBox. But things will be a little bit slower because we're running it on a website that's about to go out of business. All right, so you can choose whatever you want here, email, Shriner email or whatever to make your account. I'm just going to do GitHub because I haven't done this yet, so this will hopefully make a new account for me. I think it recognized my account. So when you click it, then yeah, it's going to come up. There'll be a license agreement for you to agree to, and then you just got to put in some basic information. You can just put, if it asks for your organization, then you can put Shriner. And yeah, you could be an assistant professor of math too if you want, as far as JuliaBox goes. Okay, so once we're in here, then we're going to want to upload our Julia notebook. All right, so you're going to want to click on the launch button. It may take a little bit for it to populate, but hopefully I'll look into that to make sure that things are working. Alright, so it took a couple of minutes to finally open, but you'll get a screen like this. Of course, I've got a lot of stuff in here, which you shouldn't have anything yet. But you can save your files on here, at least for a little while anyway. Alright, so then you're just going to go here to upload, and now's where you just find the starter code, upload. And so then I'm going to find it. I don't know where it went for me. There it is. Okay. Should be easier for you. Alright, so we're finally in, and we've arrived at an interface which is called a Jupyter Notebook. Jupyter up here, which allows us to mix writing in the form of what's called Markdown with code. So this is a code block. You can see it designates here. This is a Markdown. So you can write whatever you want in the Markdown. You can see that I've written directions and tutorials and things in markdown boxes, and then I've got my code ones. So I'm going to go ahead and start running this first code block here, because this will actually take a little while, just because of the fact that JuliaBox is free and not so great, and that Julia takes a while to load libraries. So the expectation here is that you're going to read through this stuff, and then I've given you most of the code that you want. And what I'd really like you to get out of this is how to translate what you know about differential equations, translate that into a computer input, and then be able to simulate those systems using this industry standard software here. Okay, so you can see, so when I ran this, there was a little star there letting me know it was running, and now I can see that it's done. And the thing that will trip you up, so pay attention to this, is that if you save this and then close it, come back later or something, you'll still have to start and run each one of these again, right? So like you'd have to go here and do Shift Enter here, or by the way, you could click the Run button. There. So you can see it's running, waiting, and then when it finishes, there'll be a number that appears here to let me know. See, this is the second box that I've run during this session, so it's 2. Well, the second time I've run a box. Okay, so be careful of that. But then, as you go through, right, so you can see the first example that we go through is the harmonic oscillator. And so what I'm showing you here is, so here's the math equations, right? It's a second order ODE for a spring harmonic oscillator, spring constant K. We can rewrite that as 2 first order differential equations. And then this is how we would put this into Julia. So I need to specify a function that gives me the right-hand sides here. And so they always have this same format. So I'm going to call it spring because this is a spring harmonic oscillator system. This is just the name that you're going to use for your function. So function, spring, and then you're going to put du, which is the vector of left-hand sides, u, which is the states, right? P, which are parameters, and t, so you can put in things that are directly a function of time. So the first element, the first listing for u, the u vector is x. I'm going to call it x, and then v, and then my first, there's only one parameter here, so p1 is k. And then this is where these look familiar, du1, so that's x. So dx is v, and du2, which is v, is minus k times x. Right? So I put in the system, I define some initial conditions. So this says the initial conditions are 0.5 position, 0.5 velocity. I'm going to solve it over the time interval from 0 to 10. Notice on this that there's parentheses instead of square brackets. That always trips me up when I'm doing this. So just be careful of that. And then parameters, you're going to put them in as a list. In this case, our list only has the one element, so I'm going to do a spring constant k of just 1. All right, and then that defines everything you need to know about a problem, right? I mean, so it's just, you know all those things, and those are listed in your MyOpenMath problems or whatever, but this is how you tell Julia that information. Okay, so then you're going to create an ODE problem. So this lets Julia know that we want to solve a differential equation. This is your right-hand side function, spring. Initial conditions, so you got to tell it where to start from. There's our list there. Our time interval, 0 to 10. And then the parameters come last. The list of parameters, 1. And then you solve it, right? So this says solve this system, and this is our solution, spring solution. Solve that problem, and this is the numerical algorithm that it uses to solve it. So there's a little discussion of that. The one that you've done by hand is Euler's method, right, which is relatively simple, but it's not a very good method. Nobody should use that in practice. to solve these systems. So this is a much more advanced solution that's going to have give you much closer approximation. All right, so now that we've kind of gone through that, Shift Enter. I'm going to let that run. And so what this will do is define the system and solve it. Oop, it's done. Great. So then I'm going to go to the next one, and you can see, oh. So this one will probably take a second actually, just because the first time you plot something in Julia, it takes a minute to really get all the plotting stuff in. By the way, you can kind of queue these up if you want to. You don't have to like just stare at it. So now it'll run this and this one. All right, so what did I do here? So I just took my solution. So if you just put that into the plot function, and I added a title to be an overachiever, but you didn't necessarily have to do that. You can see that just makes a title in the plot. It's going to plot the two variables, right? So U1 and U2, where U1 is X and U2 is V, as a function of time over 0 to 10. Why 0 to 10? Well, that's the interval that we told it to solve. Right? So if I went back up here and made this 0 to 20, see, the second time it goes much faster. So then 0 to 20, now I've simulated out to 20. Right? So that's a super nice way to plot it. The other thing that we might want to do is do a phase plane plot of this. So if you remember, a phase plane plot would be where time, you're doing a parametric plot, or a parameterized plot, where time is extracted, right? So we're going to plot position versus velocity. So our first variable versus the second, which traces out, in this case, a circle, right? And so that can be very useful for detecting cycles and fixed points and all kinds of things, right? So it's another useful way to look at your system. All right, so then we're going to go to one that maybe you've, the simple harmonic, we didn't really need a computer to solve. This one we don't really need either, but given all the pain that you guys have done in terms of solving these by hand, I think it's you understand just how difficult it is to solve this differential equation by hand. So let's see how we can simulate it in Julia. And so this is a damped, so this G here is a frictional force. This is our harmonic oscillator with friction, and then this is a forcing frequency. So this is somebody pushing it periodically. And so this is a very common system to examine in engineering. So same pattern again, right? So damped force oscillator, du, u, pt. You can see it's the exact same signature, same order and everything. This is very formulaic that way. And I'm just calling it something different because this is a different system, right? And then, so I'm going to say that my first element is position, my second element is velocity. My parameters now, there's more than one. There's K, G, F, and my frequency omega naught, or W naught, shorthand. So this is how you can drop those in there. And then du1 is V, du2 is given by this. Set up my initial conditions, let's just start at the same place. I'm going to go from 0 to 50 this time. My parameters are now, since there's 4 of them, I have to set them up. So this says K is 1, G, the frictional force is 0.1, the forcing F is 0.5, and omega naught is 0.9. And then I'm going to ODE problem, same setup as before. I'm going to solve it using the explicit method TSIT. Great, it's done already. You can see how fast Julia can be, even on the free version of JuliaBox. Boom, right? And then I just throw it in here and I do a plot. So we'll see more about this in a second, but so you can add things to plots. So this says if you put an exclamation point after one of these things, then it says add to the plot, right? So it kind of adds on. So maybe I'll see if I can do one. So if I wanted to add an X label to this plot, then I could do X label, and I'm going to change it from T. You can see it automatically labels that one. I'm going to change it to time. So if you put the little exclamation point there, then it says, for the current plot, add that on, right? So this is going to be useful if we want to plot more than one trajectory on the same plot. But you can see, so what's happening here, where you've got some damping of it, but then it's going to grow because we're forcing it at a frequency that's close to its natural frequency. So that's what's called resonance. All right, so we've finally arrived at, you can see that a lot of this assignment is the tutorial. We finally arrived at a case where I want you to actually solve something. So I tried to make the questions very well labeled. What you're going to do is then fill into this code box whatever you need to answer the question. Generally, it's going to be a plot or something. And then you'll do Shift-Enter on it to run it to make sure that it works, right? So these, by the way, that if you put the hashtag there, then it's what's called a comment in a programming language, and it means that you can write whatever you want there, and Julia will ignore it, right? So I think you can probably see, I guess I steered away from doing, yeah, so this is a comment. So if you want to write stuff inside of your code blocks, then you can that way. Okay, and you can see I'm just using them as like little clues or whatnot. So all I've asked you to do here is change the one parameter first, the forcing frequency, and make a plot, right? So what changed about the dynamics? You can answer that by doing a plot. So maybe if you're still watching here, I'll give you an assist, right? So a lot of this, much of dealing with computers is learning how to copy and paste effectively. So all of that stuff is defined because I've run this up here already. If you haven't, then you need to run that for this to make sense. And then I'm going to change omega naught, which I think is this parameter, the last one. So it was 0.9, I'm going to change it to 0.2. So I'm going to redefine this, I'm going to solve, and then let's make a plot of it. Alright, yeah, so we can see that so this is all I would be looking for in a solution to this first problem here. And the next one is to change the initial conditions. Okay, so then, you can see we're just going to go through some different models here. So the next one is one of my personal favorites, which is a predator-prey, Lotka-Volterra predator-prey equation. We studied the competition model earlier in the semester, but this is for, rabbits and lynx or rabbits and wolves or something where they're very dependent on one another, or the predators pretty much only eat one species of prey. Okay, so here I ask you to make a phase plane plot of the dynamics. So remember, these are time dynamics plots, which are super useful in themselves. To do a phase plane plot, you do the plot, but you do vars 1, 2. So this says plot the first variable against the second. So, and that's going to be, it's a cool plot for the Lotka-Volterra predator-prey. All right, and then, just because I can here, I had to do a little chaos. Talk a little bit about chaos. So this is the Lorentz system. So I define it for you here. By the way, so Julia is kind of nice for math stuff because you can actually use Greek letters. I kind of avoided it above, but you can type in these Greek letters if you ever needed to. So you just do backslash, so to get the Greek letter sigma, backslash sigma, and then hit tab as soon as you finish, and it'll convert it to a Greek letter. Which just makes so there are math equations that we write look like the things we put in, which is just sort of convenient. So anyway, this is a system that demonstrates a property called chaos, which I defined for you up here. And So we're going to generate some cool plots of it and just illustrate some of the characteristics of chaos. So you can see you can do a three-dimensional plot very easily in Julia of the dynamics. And so this is a very famous plot, obviously. You may have seen it before. One of my personal favorite plots of all time. So we start here, and then this is what's called a strange attractor that it's tracing out here. And to me, it kind of looks like butterfly wings, but you can decide that on your own. So this demonstrates the concept of sensitive dependence on initial conditions. So we start two initial conditions very close to each other. You see our initial conditions now have three elements because the Lorentz system is three-dimensional. So I start two of them very close, so they stay close for a while, and then all of a sudden you can see that they go completely different, right? So now after about t is 15, you lose all ability to forecast one versus the other. And so that's what's meant by that sensitive dependence that chaotic systems have, to where it makes them fundamentally unpredictable in their dynamics. All right, and then a couple of questions left here for you to wrap up. My hope is that you'll get something out of this project, but it won't be, we've done enough in this COVID-laced spring semester here, so I figured we'll coast in here a little bit. So anyway, if you have some problems, let me know. But hopefully you can figure out the technical aspects of it pretty easily watching this video. And thanks for sticking with me throughout this long semester. I miss y'all, and hopefully I'll see you in person very soon.